thanks for tuning in to the Oxygen Alliance YouTube channel, where we share the Concentrator Talk virtual meeting hosted every Thursday from 2 to 3 p.m. Central African Time. In the talk, we discuss different aspects of oxygen concentrator assessment, use, and maintenance. And please don't forget to subscribe and hit that notifications bell.
Hello everyone. Thank you for joining us for week 36 of the Oxygen Concentrator Talk Call. My name is Sharon Ngozo and I'm currently in Lilongwe, Malawi, and I'm pleased to be hosting the call today. Today I've been joined by my colleague Mawe Lungu alongside our usual technicians from OpenO2 and Sunlight. On the technicians panel today we have Masofa Mojaji, Kowinda Singh, Francis Sabani, Linda Mission, Daphne Magela, Fatani Damandikani. In case you're just joining us for the first time, be aware that the Concentrator Talk is a virtual meeting that the Oxygen Alliance hosts every Thursday from 2 to 3 p.m. Central African Time, where we talk about oxygen concentrator assessment, maintenance, and use. If by any chance you have any problem concerning oxygen concentrator maintenance or assessment that you might need help with, we encourage you to send in advance to ask your questions via our email info@oxygenalliance.org. And during the call, maybe you have some questions for us concerning the questions that we'll be discussing. Feel free to paste your questions in the chat, or you can raise your hand and you can ask your question. As usual, today we also have the topic of interest. And today, Fatan will be talking about the power protective for oxygen concentrators. So now to jump into our questions. Our first question says, I have started working as a technician. I have observed that during servicing of the oxygen concentrators, Zoride is refilled in both of the Zoride molecular sieve beds. If there isn't enough Zoride to refill 2 sieve beds for a concentrator, can you may refill one with Zoride? I'll ask Linda to answer this question.
Thank you, Sharon. Refilling one sieve bed with zeolite will likely contaminate the sieve bed with new zeolite. If 2 sieve beds, one of which contains old zeolite and the other fresh zeolite, are combined to work in an oxygen concentrator, during the pressure equalization and paging phases, moisture and dust might transfer from the bed containing old zeolite to the bed containing new zeolite. In order to raise the pressure of a depressurized bed, pressure equalization allows air to move from the bed that is being fed to the bed that was being paged by venting the sieve bed to the atmosphere. Nitrogen molecules are adsorbed during the paging process. So in your situation, I advise waiting until you have enough zeolite to replenish both sieve beds. Even if there is just one sieve bed which is damaged, you have to replace the entire pair of the sieve beds. Thank you. Back to you, Sharon.
Thank you very much, Linda, for that answer. Any questions from the audience or comment? Okay, if we have no questions or comments, we move on to our next question, which says, hello, I'm a technician at a certain district hospital. I'm aware that all concentrators have oxygen sensors installed in them. Why is it necessary to test an oxygen concentrator with an analyzer again when they already have inbuilt oxygen sensors? I'll ask Francis to answer this question.
Thank you, Sharon. So you're right that all concentrators have an inbuilt oxygen sensor, and these measure the oxygen concentration being produced by the concentrator itself. If the period is below the recommended range, a signal is sent and an alarm is raised. And also what follows that is a low period LED, which then turns on. As long as the concentrator keeps running, the oxygen sensor is always measuring the concentration, but there are times where the the sensor can send wrong signals to the board, triggering an alarm accompanied by an LED showing low purity when the oxygen concentration being is within the produced is within the recommended range. Though it happens rarely, the only way to find the problem is by having an oxygen analyzer and testing the purity of the concentrator at the patient's outlet. There are also instances where the concentrators keep running and can't raise an alarm even when it's producing 21% of oxygen purity. So in this scenario, the sensor isn't sending a signal to the trigger or buzzer and the low purity LED. So we have come across both these instances a couple of times. Having a handy oxygen analyzer at every happy facility is really important because it makes you easier to trace these problems and sort them out rightly. So if you can afford to purchase one, then you can just build your own ultrasonic oxygen analyzer. Thank you, and back to you, Sharon.
Thank you very much, Francis, for that well detailed answer. Any comments or questions from the audience? Yes, Fatan.
Thank you. I have a question. Can a faulty oxygen sensor affect the purity that you measure from an oxygen concentrator?
Francis, are you comfortable to take that?
I don't know if I got the question right, but what I heard was can something like, okay, basically a sensor can't, we just sense the purity of the oxygen that is passing through it. So it doesn't have to do anything with the purity. It just measures it. So maybe if you repeat the question, or maybe I didn't get it rightly.
Well, you have answered the question because I was looking if a photoxin sensor can affect the purity. So you have answered that it doesn't affect the purity. So that's okay.
Maui, you have a hand up.
Yes, just to add on to what Francis has just said, but I think it also depends on what type of fault is associated with that sensor. Because if the sensor has a leakage somewhere, then it will definitely affect the purity. So as long as the fault within the sensor is electrical, then it won't affect the purity. But then if there's a leakage somewhere or there's a loose connections within the sensor, then it will affect the purity.
Thank you very much for the answers. So for those who are interested in building a handheld oxygen analyzer, you can visit the Oxygen Alliance website. There's a special topic that we did on all the tools you might need to build an oxygen analyzer. So it might be helpful for you. So now we move on to our next question, which says, what are some of the safety tips one should consider before starting to work on oxygen concentrators and also during oxygen concentrator repairs? I'll ask Linda to answer this question.
Thank you once again, Sharon. There are a number of safety factors that one should consider when working with oxygen concentrators. Some of the factors that should be considered for the safety of the machine as well as the personnel working on the machine are as follows. Always disinfect the oxygen concentrator before starting any maintenance work. And also wear surgical gloves in order to prevent infections. And you should also check the power rating for the oxygen concentrator being worked on before plugging it in into a power source to avoid burning some electrical components in the machine. And in order to increase the runtime and increase the lifespan of a concentrator, make sure that intake and the cabinet filters are always clean. The filters should be cleaned weekly or even twice a week if the concentrator is used in dusty environment. Another important factor to consider is the type of tools used during maintenance. This is one of the things which is mostly overlooked by the technicians. Using wrong type of screwdrivers results in damage to the screw heads, and if the screw heads are damaged, you may not be able to service the machine again, as it may be hard to even open the concentrator. So always use the right type of screwdrivers on the right type of screws. And also checking for leakages is one of the things what we do mostly when working with concentrators. So when using soap and water to check the leakages, um, since the concentrators are electrical equipment, you should always be careful when applying soap and water on different components in the concentrator so that you do not spill any water on the electronic components. And always have a cleaning cloth for wiping the soap and water. Another thing is when servicing an oxygen concentrator, never leave the tubings connected to either ends of the sieve base disconnected. Leaving the sieve base disconnected or open, even for a few seconds, exposes the zeolite to moisture. As such, the performance of your concentrator is affected. So always seal the ends of the sieve beds whenever you disconnect the tubings using cell tape. And finally, oxygen supports combustion. Hence, you shouldn't expose an oxygen concentrator which is running to any open flames, as this may cause fire. Thank you.
Thank you so much, Linda, for the well-detailed answer. Though I have a question for you. You have mentioned about disinfecting the concentrators. How should the disinfecting concentrators be like? Should you have like a soap and water and have a brush where like you have to clean the whole concentrator? Do you need a wet cloth to clean the concentrator, or do you just need a spray bottle when disinfecting the concentrator?
Okay, thank you for the question. You can use a damp cloth to wipe, just to wipe the outside of the concentrator. You can dip the cloth in a disinfectant, and then it should be damp, not very wet, and then just wipe the outside of the concentrator.
Thank you very much, Linda. Fatani, you have a hand up.
Yeah, I have a question. So, Linda, you've talked about damaged screw heads. So, in case you have a stuck screw because of, say, a damaged screw head, is it okay to use penetrating oil to loosen the screw?
Thank you, Fastan, for the question. As we have already said that oxygen supports combustion. If you use penetrating oil, something which is flammable, when it comes in contact with oxygen, it may cause fire. So it's not a good idea to use penetrating oil. Thank you.
Any other question for Linda or comment? If we have no comments, we have a poll at the end of this question. I'll ask Maui to launch the poll and explain how to access.
Thank you very much, Sharon. So I will be launching our first poll of the day. And the poll says, have you ever come across a concentrator with a damaged screw head? So I'm going to leave the poll open for people to vote, and then I will explain the results later. So for those of us who are joining via our computer, if you go to the bottom right of your screen, the icon on the far right is the activities button. So if you click on that, a window opens up where the activities menu is one of the, the pause menu is one of the listed options. and that's how you get to the pause. If you're joining us from your mobile phone, then you click on the options menu, and then a window will open up where the activities button is one of the options. If you click on the activities button, it's going to take you to the pause menu. So the votes are coming in, and it seems all of us have ever encountered this problem. So I guess this is something that we normally encounter. So yeah, I will end the poll now. Back to you, Sharon.
Thank you very much, Mai. So now we'll move on to our next question, which says, I'm a biomedical intern at a certain hospital, and I'm currently working on the DeVilbiss 525 concentrator. This concentrator was brought to the workshop because it was found to be producing low oxygen purity during last week's concentrator assessment in the ward. When I removed the covers of the concentrator, I noticed that the rotary valve was not rotating. What troubleshooting steps should I take to assess it if the rotary valve is faulty? I'll ask Masofa to answer this question.
Thank you, Sharon. There are a number of things that are likely to cause a rotary valve to malfunction. This includes a fault on the PC board, broken wire harness which connects the rotary valve to the control circuit board, and also a rotary valve itself could be faulty. To successfully identify an actual cause of your problem, you will need to check the above mentioned components one at a time. You can start with checking the wire harness if it's broken or not. You can check it visually or mechanically, yes. The wire harness has 9 lines to use multimeter. So use a multimeter to check the continuity of all the lines. If all the lines are in good shape, then you can proceed to the next component, which, if you found that some lines are broken and the damage is visible, you should reconnect the lines by soldering and using either a heat shrink or insulation tape to seal any exposed wires. Sometimes the problem can originate from the control board. The 2 revolving discs inside the valve are controlled by the step motor, which then is powered and controlled by the control circuit board. Therefore, you need to check the voltage of the stepper motor windings in order to determine if the problem is in the control board or your valve. The voltage can be checked either on the wire harness connectors on the valve or the printed circuit board using the voltmeter. The table in the graphics show the combination wires you should be testing the voltage on, which lead of a voltmeter should be placed in particular lines of the wire harness during test. If you do not obtain any of the voltage readings as shown in the table, and the wire harness is intact, then you should replace the control circuit board. However, if the wire harness is okay, you have done the voltage test on the PC board connector, those voltage readings were obtained, then the valve itself is faulty and should be replaced. Thank you, Sharon.
Thank you very much, Masofa, for that explanation. Any additional comments on what Masofa said or any questions for him? If we have no question, we have a poll at the end of this question, and I'll ask Maui to launch the poll.
Thank you once again, Sharon. So we'll be launching our second poll now. So the poll says, have you ever troubleshooted a rotary valve before? So for those of you who, well, maybe let me wait till people vote before I talk about the next part. So I'll just give it a few seconds. Okay, it seems the votes are coming in. We have more people who have ever worked on the rotary valve and only one who hasn't worked on the rotary valve before. So I'm going to end the poll now. So I was trying to say that we have a video that we made at the Oxygen Alliance on how to troubleshoot, clean, and repair a rotary valve. So for the person that voted no, I guess you need to go on our YouTube channel and have a look at that video. And I'm sure together with the explanation that Masofa gave, that will help you to work on troubleshoot the rotary valve. Back to you, Sharon.
Thank you very much, Mali. Okay, now we move on to our next question, and it reads, I'm a biomedical technician working on Devil-Breeze oxygen concentrator circuit. After a series of troubleshooting endeavors, I have found out that the fuse on the control board is blown. The fuse is rated 80 milliamps, but I only have a 100 milliamps fuse in the workshop. Can I replace the blown fuse with a 100 milliamp fuse? I'll ask Gowinda to answer this question.
Thank you, Sharon. To regulate all concentrator operations, each oxygen concentrator has a circuit board with a microcontroller. The printed circuit board contains a variety of electrically sensitive components, including resistors, transistors, varistors, diodes, capacitors, and light emitting diodes, fuse, etc. The electrical needs for oxygen concentrator are typically 230 volt AC at 50 Hz or 110 volt at 60 Hz, depending on the country power supply rates. So power systems are dynamic by nature and are expected to fluctuate while in use. However, variations may be more severe and last longer than what electrical equipments, including concentrators, can tolerate. Medical equipment failure and malfunction are recognized to be mostly caused by inadequate main power supplies. So power supplies from the main can result in corresponding current spikes that can damage the circuit board system. The function of a fuse, therefore, is to break the circuit if a fault in an appliance causes too much current to flow. So that may be overload. So this protects the wiring and the appliance if something goes wrong. The fuse contains a piece of wire that melts easily if the current going through the fuse is too great. The wire heats up until it melts and breaks the circuit. So to test if a fuse is working, we can use a multimeter to set at continuity mode. Put the multimeter probes on the end caps of the fuse. If the fuse is fine, you will hear a beep sound from the multimeter. Otherwise, if the beep sound is not coming, the fuse is blown. So the rating of fuse is usually maximum current that the control board or device can handle. Replacing a lower rating fuse with a higher rating fuse, a larger current that is more than the maximum will be allowed to pass, and this can damage some components on the control board. Therefore, therefore it is not advised to replace a higher rating fuse for a lower rating one. Thank you, Sharon.
Thank you very much, Gowinda. I have a question for you. Would you recommend a technician using a wire instead of a fuse on the PCB board of an oxygen concentrator?
No, we should not use the wire because that is the same as answered in the question. No? So it will allow more current to pass through it. So that can damage the other components also. So it is best to use a power stabilizer with the machine to overcome this type of problems.
Thank you very much, Govinda, for that answer. Okay, any comments or questions? Okay, if we have no questions, we move on to our next question, which says, during last week's concentrator talk, there was mention of carrying out a pressure test after refilling sieve beds before putting them back into the oxygen concentrator. I wanted to know how to carry out the pressure test, the necessary steps, and the tools that are needed. I'll ask Daphne to answer this question.
Thank you, Sharon. So this is a very good question, and you're right. Last week it was mentioned that after refilling the sieve beds, it is important to pressure test them before putting them back into the concentrator. So the pressure test is carried out to test if the sieve beds will leak under certain pressures, allowing you to eliminate any leakages that might be there. It is also important to note that the pressures used when performing the pressure test vary depending on which model the sieve bed was taken from. For example, for the DeVilbiss 5 to 5 models, as the pressure rises and falls during the cycles, the pressures will approximately be 25 to 30 psi, so the tests are carried out at 30 psi. Other sources of leakage can be the size of the sieve bed end caps. So on the graphics on the left, that's you see the sieve bed, and the top, that's where the end cap is. So if the sieve bed is not properly closed or the O-ring has degraded, it can be leaks. So in the case where the O-ring has degraded, you can fix this using thread tape, or you can just open the end cap, the sieve bed, and close it properly to stop the leakages. Other models, such as the ASF, have washers. So on the right, we see the black sieve bed. It has a washer on the top. This is another source of leaks. These washers have gaskets underneath, which degrade over time and can be a source of leaks, as I said. So if there's a leakage because the washer has degraded, you just add thread tape. But if it wasn't tightened enough, if the nut on top wasn't tightened enough, you just tighten it. So leakages in the sieve beds is one of the major factors that affect oxygen purity of oxygen concentrators. Leakages allow ambient air to enter the sieve beds, contaminating the zeolite, hence reducing its absorption capabilities, leading to low oxygen purity. The process of refilling sieve beds is carried out in a room with the humidity below 45% in order to avoid contaminating the zeolite. And since the pressure test is done soon after refilling the sieve beds, it is always best to carry out the test in the same conditions where the humidity is below 45% for the same reason. So the tools that are needed for the pressure test include an air compressor, pipes, a gate valve, water separator, one-way valve, spanners, thread tape, soapy water, and a wiping cloth. So these are the steps to carry out when doing the pressure test. Firstly, you have to attach a pressure gauge to the top of the sieve bed so that you're able to tell the pressure in the sieve bed. For example, with the DeVilbiss models, that means you need the pressure gauge to be able to check if the pressure has reached 30 psi. It would be easier if your pressure gauge is in psi so that it's easier for you to tell, and if the resolution isn't too big so that it's easy for you to observe that it's at 30 psi, for example. Secondly, you attach the pipes from the compressor to the bottom side of your sieve bed. So on the right of the image in the graphics, you will note that the pipe from the air compressor is attached to the gate valve. And then after the gate valve, there are two water separators. So the gate valve is used to stop the airflow once the pressure in the sieve bed reaches the target value, and the water separators trap water and prevent moisture from going into the sieve bed. And once the pressure reaches the target pressure, the gate valve is closed and the compressor is switched off. You then apply soapy water at the bottom of the sieve bed where the end caps are and observe for leaks. If there are leakages, like I said, this can be solved by tightening or adding thread tape to create a tight seal and carrying out the pressure test again to check if the problem has been solved. Thanks, Sharon.
Thank you very much, Daphne, for that well-detailed explanation. Any questions for Daphne or additional comments? If we have no comments and questions, we have 2 polls at the end of this question. I'll ask Maui to launch the polls.
Thank you, Sharon. So we have 2 polls relating to Daphne's explanation. So I'm just going to launch them both, and then people can vote. So the first one says, have you ever carried out a pressure test before? So I'll leave that open. And the second one also says, have you ever had an experience where your sieve beds were leaking after refilling them? So also leave that open and then have people vote. Okay, so for the first poll about the pressure test, it seems most people have done that, but we still have a few who have never done a pressure test before. So I guess Daphne's response has helped you understand the pressure test process better. For the second one, it seems all of us have ever experienced leakages with the sieve beds. This is something very common. So yeah, thank you very much. Back to you, Sharon.
Thank you very much, Maui. So reaching this far, we'll take a slight diversion to today's topic of interest. So Fatani will be taking us through today's topic of interest. So Fatani, over to you.
All right. Thank you, Sharon. So in our today's topic of interest, we're going to look into power protective measures for oxygen concentrators. So power quality problems are a very common occurrence in most developing countries, and these problems have a significant impact on oxygen concentrators as well. Depending on the country's voltage standard, oxygen concentrators need either 230 volts at 50 Hz or 120 volts at 60 Hz. And when in use, the main power supply is prone to fluctuations. Poor mains power supply is one of the main causes of medical equipment failure and malfunction, especially oxygen concentrators in low and middle income nations. Therefore, finding power safety precautions for oxygen concentrators is very crucial. The power quality consideration to take into account when choosing a solution for low power quality and power protective measures for oxygen concentrators are what we are going to discuss today in our topic of interest. So now let's look at power quality, what power quality is. So basically, electric power quality is the degree to which the voltage, frequency, and waveform of a power supply system conform to established specifications. In simple terms, power quality, you can think of power quality as the compatibility between what comes out of an electric outlet and the load that is plugged into it. So this load can be an oxygen concentrator, for example. Now, power quality can be grouped into 2. We have good power quality and poor power quality. So good power quality can be defined as a steady supply voltage that stays within prescribed range, steady AC frequency that is close to the rated value, and also a smooth voltage curve waveform. So this waveform has to resemble that of a sine wave. So if you take, for example, an oscilloscope and plug into your outlet and you see a smooth sine wave, then you know that your power quality is good. Also, good power quality is that power that delivers enough current under any operating conditions. It might include minimal but not damaging changes. On the other hand, poor power quality is power that is delivered to a load that includes excessive or damaging changes such as voltage drops, voltage unbalance, voltage fluctuations, current unbalance, transients, and also harmonic distortion. Now, having talked about poor power quality issues, let's look into brief detail what poor power quality issues we face in most developing countries. So the first power quality issue that we're going to look into is outages. So what is an outage? A power outage is when the electrical power goes below 50% of its nominal line voltage for more than 10 milliseconds. For the case of Malawi, we have a nominal voltage of 230 volts. So if that power goes to 50% of it, which is 115 volts for more than 10 milliseconds, then we consider that as a power outage. Now, power outages can also be grouped into two. We have short duration power outage that occur when switching between grid electricity and backup power. And also we have long duration power outages, and this can last from minutes to hours. This usually prevent the use of an oxygen concentrator. Now, in both these cases, in both short and long duration outages, when the power returns, there can be damaging voltage spikes, and oxygen concentrators should be protected from these. The second power quality issue that we're going to look into is overvoltage. Now, an overvoltage is when the voltage remains high for an extended period of time. These levels of voltage for such extended periods of time can lead to high currents and the permanent damage of oxygen concentrators. Moving on, we're going to look into frequency fluctuation. Frequency fluctuation is also another poor power quality issue that many developing countries face. Frequency fluctuation. So there in the graphics you can see that's for a graphic for power over voltage. Now we're looking into frequency fluctuation. So frequency fluctuations are fluctuations in the cycling rate of the alternating current. So most countries, including Malawi, we use 50 hertz. Now these changes in frequency can affect the rotational speed of the motor in the compressor, and this can reduce the efficiency of the compressor and consequently affect the purity of oxygen from oxygen concentrators. So if you see in the graphics, you have that narrow yellow band. That band is for the normal frequency, which is 50 hertz. And above it, you can see frequencies spiking to 50.15, which can be dangerous to concentrators. And also on the bottom, you can see frequencies going down to 49.85%, which is also damaging. As also I already said that they can affect the rotation speed of the motor. The other poor power quality issue that we're going to look into is called a voltage sag. Now, a voltage sag is a reduction in the mains voltage, which lasts longer than 10 milliseconds. Now, this reduction can be less than 90% of your nominal voltage. Now, this can be caused by a large number of electrical loads being switched on and thereby overloading the grid. So you can see also in the graphics, that's a waveform for a voltage sag. You can see a normal peak, power peak that is shown in red, and there you have a voltage sag whose peak is shown in orange. Yeah. So that's a voltage sag. Have a voltage reducing its peak voltage. Now, during a voltage sag, the motor might stop running. The result of this is not that the oxygen might stop flowing, but also the current will still be drawn by the motor with a low voltage, but then the current will still be drawn by the motor. Now, this can result in the coils overheating, which can lead to the seals of the compressor. You have the gaskets, the O-rings. These can fail due to overheating. And over time, the motor coils might also burn out. Moving on, we're going to look also into voltage surges. The voltage surges is also called voltage swells. Now, a voltage surge, this is when the mains voltage increases beyond 110% or the nominal voltage. For example, if you have a 230 volts power supply, 110% increase will be greater than 253 volts. And this can last for less than one continuous minute. You can see a voltage surge in the graphics. So severe voltage increase can cause oxygen concentrators to draw too much power, which can lead to damage of the microcontroller as well as the compressor. And the other poor power quality issue that we're going to look into is voltage spikes. Wind already talked about voltage spikes when he was explaining about the use of the fuse. Now, what are voltage spikes? So voltage spikes are transient voltage disruptions lasting less than 10 microseconds and can be a sudden increase in peak voltage. So we have, for our case in Malawi, we have a peak voltage of 230 volts. If that peak voltage increases suddenly, can go up to 500 volts. That is what we call a voltage spike. So they differ from voltage surges in that they are short-lived, and these large spikes can be damaging to sensitive electronics such as microcontrollers and circuit boards. And this is the most common failure mode of oxygen concentrators due to voltage spikes. So in the graphics, you can also see a plot of a voltage spike. And that spike, the spike is going to 250 volts from 230. So that can be damaging to oxygen concentrators. Now, what happens if we fail to protect oxygen concentrators from poor power quality issues? We are all aware that we have in an oxygen concentrator have microcontrollers, compressors, which are some of the most crucial components of oxygen concentrators, and these are typically destroyed by poor power quality issues. And this can lead to a significant number of concentrators being damaged if precautions are not taken to protect them. So depending on a number of factors, there are measures that can be taken to protect oxygen concentrators against poor power quality issues. Some of these factors we have, you can look at how frequently do you experience power failures. You can also have, you can also look into a factor like how long do the power failures last, and also how poor is the electrical supply, and what options do you have in terms of power supplies. Do you always rely on grid power, or do you have backup gensets or batteries or solar power? So you can have different options of power supply. Now, having looked at different poor power quality issues, now let's look at technologies or measures that we can use to protect our oxygen concentrators from power quality issues. The first technology that we can use is that protects our concentrators from over and under voltages. Now, these technologies are used to protect your concentrators from over or under voltages. You can see that technology is in the graphics. It looks like that. And these devices, what they do is they cut off the power when the voltage goes below or above a set threshold. So you can see it, for example, you can say that if my voltage goes above 240 volts, this device should disconnect the power from the concentrator. Or if it falls below, say, 200 volts, it should also disconnect the concentrator from the main power supply, thereby protecting your device, your concentrator. So these devices are to be installed between the main power supply and the concentrator. Now, the oxygen concentrator is disconnected to protect it when the voltage falls below or goes above a set threshold. That can be damaging to our concentrator. Secondly, we are going to look at how we can protect our oxygen concentrators from voltage spikes. So there are various types of protectors for large voltage spikes. Some of them, they divert the current to earth, thereby shorting the current, and others dissipate the current as heat. Now, the most common approach to protect concentrators from voltage spikes is incorporated right on the board in form of MOV. So MOV is an abbreviation for metal oxide varistor. So MOVs are a very common product used to protect oxygen concentrators from voltage spikes. An MOV contains a semiconductor material which begins to conduct at a certain voltage threshold, allowing power to be either diverted to ground or converted to and dissipated as heat. Many of us might have seen this component on circuit boards. It's called an MOV, metal oxide varistor. So the function of it is just to protect our devices or concentrators from voltage spikes, as I've already explained. The other protective measure that we can look into is startup delay devices. So when the power comes back after power cut, there can be large surges. So I've already explained about voltage surges or swells. So these large surges can be damaging to oxygen concentrators. So to protect our concentrators from this, we can make use of startup delay devices. So these devices, they cause a brief delay in reconnecting the concentrator to the mains power. These surges and spikes are known to frequently occur during this startup phase. Additionally, a delay prevents the appliance or the concentrator from being continuously turned on and off during fluctuations. So in the graphics, you can see a device that is called a startup delay device. So you plug in your device there, and it's gonna do the delaying for you when the power returns after an outage. Then we have what is called voltage stabilizers. Wind also mentioned about voltage stabilizers in brief. So a voltage stabilizer particularly resolve the voltage sags and surges by stepping up or down the voltage to deliver a constant 230 volts supply to the concentrator. So when the voltage exceeds or falls below the required operating voltage range, the stabilizer is used to cut off the power to the concentrator, thereby protecting your oxygen concentrator. So basically, this one is just delivering a constant 230 volts, regardless of what is coming out from the outlet that it is plugged into. As long as it's plugged into that outlet, whether the outlet is giving 230 volts or more, or less than 230 volts, this device will supply to your concentrator a constant 230 volts. So you can also make use of that. It's a very important device. Lastly, we're going to look at the UPS device. UPS, an abbreviation for uninterruptible power supplies, is used to provide an uninterrupted power to devices when the primary power is disrupted for a short duration, typically less than 1 hour. And this can provide temporary power stabilization, and it is often used to bridge the time between the grid power supply going down and the generator starting up. So UPS devices automatically determine whether to draw power from batteries or from the grid. They also sometimes may contain circuitry to detect when there are problems with the grid power. These problems can be over voltages, under voltages, outages, and then they manage this using, they also have inbuilt voltage stabilizers. Sometimes they might also contain voltage surges. So thank you. That was all I had for you in our today's topic of interest. Thank you for your attention, and over to you, Sharon.
Thank you very much, Fasani, for the explanation. Any questions for Fasani or additional comments? Daphne, you have a question?
Yes, thank you, Fatani, for the wonderful presentation. I've learned a lot, but I didn't really understand the difference between a voltage surge, I think, and a voltage spike. So if you could please explain more on that for me.
Thank you, Daphne, for that question. So I explained that voltage surge is when a voltage surge is when power or mains voltage increases beyond 110%, and also a voltage spike is also an increase in the voltage that is coming from the supply. The main difference is that voltage surges, they only last for a short period of time, while voltage spikes voltage spikes, they last for a short period of time, while voltage surges, they can go up to 10 minutes or more. So the major difference is the period, the time it takes for that voltage increase to prevail. So in voltage spikes, they usually take less than 10 microseconds, while voltage surges, they can go up to 10 minutes or more. So that's a major difference. But in practice, they are all an increase in the voltage from the mains supply. Thank you.
Thank you very much, Fatani. Okay, so now if we have no further questions, we move on to our last question, which says, pressure regulators in oxygen concentrators are always preset by the manufacturer to a certain value. Why is it that in some cases the pressure at the patient outlet changes, even if everything has been serviced and we have to reset the pressure regulator? What causes this change in outlet pressure of the pressure regulator? I'll ask Daphne to answer this question.
Okay, thank you, Sharon. So, a pressure regulator is a valve that controls the pressure of a fluid, in this case, a gas, to a desired value. There are two types of pressure regulators, and these are pressure reducing regulators and back pressure regulators. Back pressure regulator controls the inlet pressure. It maintains the set pressure and allows excess pressure to vent through the regulator, while a pressure reducing regulator reduces the input pressure of the fluid to a desired value at its output. Oxygen concentrators use pressure reducing regulators. A pressure regulator has a restricting element, a loading element, and a measuring element. The restricting element is a valve that can provide restriction to flow, which allows gas to flow through the regulator at a reduced pressure. The loading element is a part that can apply the needed force to the restricting element, which is the valve. So the loading element is usually a piston, diaphragm, or a spring. And the measuring element determines when the inlet flow is equal to the outlet flow, and it responds to downstream pressure and acts against the loading element to position the valve accordingly. The diaphragm itself can also be the measuring element. So in the graphics, we see the spring and the sensing the flexible diaphragm, and the diaphragm, that is the measuring element, and it can also be the restricting element. It can also be the loading element, but in the picture, the spring is the loading element and the measuring element is the diaphragm. So the diaphragm or piston, and the restrictive element together form a mechanical linkage and work together to balance the forces associated with the three devices. And these forces are the opening and closing forces. So these two forces act on this mechanical linkage, with one trying to close the valve, shutting off gas, while the other works to open the valve, increasing gas flow. Under steady operation, the sums of the opening and closing forces are always equal but in opposite direction, giving a static equilibrium condition at which the pressure reaches the set point. There are many factors that cause failure in pressure regulators, and these are damage to internal components, droop, and changes in inlet pressure. So over time, the moving parts of the regulator, such as the diaphragm, experience a significant amount of force, and they eventually succumb to degradation, making them less responsive than they should be. In other words, the older a regulator gets, the more prone it is to failure because the internal components get damaged, leading to a change in the outlet pressure. So, droop, which is also one of the things that lead to changes in outlet pressure, refers to a drop in the outlet pressure below the original set point as flow increases. The accuracy of a pressure regulator is shown by charting outlet pressure versus flow rate. So the resulting graph in the graphic shows that the drop in outlet pressure as the shows the drop in outlet pressure as the flow increases, and that's phenomenon that we call droop. Droop is not only caused by increase in flow, it can also be caused by significant changes in the inlet pressure beyond the value when the regulator output was set. So this is to say that when the pressure going to the regulator changes significantly from the pressure value that it was exposed to when setting the regulator, and this happens in concentrators. Sometimes the pressure from the sieve bed changes due to different reasons. For example, blockages in the sieve beds or faulty solenoid or rotary valves. And these changes in the pressure exposes the regulator to pressures different than the normal sieve bed pressures that were present when originally setting the output of the pressure regulator. So as the inlet pressure rises from the initial setting, the outlet pressure falls, and inversely, as the inlet pressure falls, the outlet pressure rises. This phenomenon is known as supply pressure effect or inlet dependency. The image showing on graphics also shows factors that cause droop, such as spring effect, diaphragm effect, and body effect. And I'm going to talk about spring effect and diaphragm effect. So, spring effect is the result of the reduction in spring force when the diaphragm and valve are fully down. This is because the spring requires less force to move it upwards a certain distance when it is extended compared to compressed. And this reduction in the spring force requires a lower outlet pressure to balance it, causing a change in the outlet pressure. With the diaphragm effect, as with spring effect, the wide and fully down position is again the problematic diaphragm position. The effective diaphragm area increases, giving the outlet pressure more area to act upon, which in turn means a lower outlet pressure is needed to balance the forces and reach equilibrium, therefore creating a change in outlet pressure. As previously mentioned, the set point is where forces balance and there is no movement allowing air to flow at that pressure. So these effects create a new location where forces balance, creating somewhat a new set point. Thank you, Sharon.
Thank you very much, Daphne, for that explanation. Any questions or comments to Daphne? Okay, if we have no questions or comments, we have come to an end to today's talk. So thank you all for joining us on this week's Concentrator Talk. For our new members, please share with us your contact details in the chat so that we can add you to the mailing list. So before I wind up, Maui, do you have any announcements?
No, nothing from me, Sharon. Just a reminder that next time we'll be here again, same time, 2 p.m. Central African time. So let's remember to add it on our calendars. That's it.
All right, so if you have any questions for us, we advise you to send them to us in advance through our email, info@oxygenalliance.org, and also be sure to visit our website, www.oxygenalliance.org. You can learn more about the Oxygen Alliance and the work that we do. We also have a YouTube channel where all the previous Concentrator talks are posted, so you can check it out, and please remember to subscribe. So until next time, it's goodbye.